Hello friends, I am Snehal and I am teaching you physics. Today we'll see the electric field of electric dipole at an equatorial point, and we'll also see the effect of external electric field on electric dipole. So let us start. Let's draw the electric dipole first. This is minus q and plus q. So this is electric dipole, and distance between these 2 points minus q and plus q is 2a. Suppose minus q is at point A, plus q is at point B, and this O with the midpoint of this line joining minus q and plus q. Then let's draw the equator, which is a perpendicular line passing through the midpoint, and let's choose some point on equator. Okay, so suppose this is some point on equator. Let's call it P, and I wish to find the electric field due to this system at this point P. So suppose E plus is the electric field at P due to the charge plus Q, and E minus is the electric field at P due to minus Q. Okay, so electric field due to plus Q at this point will be directed along this line because this is positive charge, so field is radially outwards, and electric field due to the minus Q at the point will be directed along this line, means towards minus Q. So let's join these points. Okay, and suppose this distance from O to P is R. This distance is A, this distance is A. So R is distance of point from midpoint of dipole. Then now magnitudes of these charges are same, and the point P is at same distance from minus Q as well as plus Q. So the electric field due to minus Q and electric field due to plus Q at that point will have same magnitude. So I can say that the magnitude of E plus bar equals to the magnitude of E minus bar. Okay, and let's call it E. Now let us draw the fields due to minus Q and plus Q. So field due to minus Q will be like this. Okay, and field due to plus Q will be directed along this line. So something like this. So this is E plus bar, and both of them have same magnitude. So length of these arrows should be same. And this one is E minus bar. And suppose this angle is theta. So if this angle is theta, this angle is also theta, because these are congruent triangles. All three sides are same and this angle is same. This is perpendicular. Okay, now let us just resolve E plus bar and E minus bar along vertical and horizontal axis. So let me draw the horizontal axis. So this component of E plus, because this angle is theta, so through the angle, this is cosine component. This is E plus cosine theta, and component along the horizontal axis this component will be E plus sine theta. Okay. Similarly, for E minus, this component, this is E minus. So this component here will be E minus cosine theta, and component here will be E minus sine theta. So we'll have this component E minus cosine theta, and this component is E minus sine theta. Okay, now as you can see, the components of E plus and E minus along this vertical direction have equal magnitude and they are directed opposite to each other. So this E plus cos theta and E minus cos theta, they get cancelled out. Okay. So components of E plus bar and E minus bar along vertical direction have equal magnitude but opposite direction, therefore they get cancelled out. Okay, and then as you can see, the components in horizontal direction, they are added up. So we have E plus sine theta and E minus sine theta in this direction. So the total electric field is in horizontal direction and it is addition of these two components. Therefore, total electric field is in horizontal direction and let's call it E equator. So E equator is the total electric field. It is equal to E plus sine theta plus E minus sine theta. Okay, and it is 2 times of, because the magnitude of E plus and E minus is equal to E, so this is 2 times E sine theta, because this is equal to E sine theta and that one is also equal to E sine theta. Now we just have to find the magnitude of E and the value of sine theta, then we'll have the value of the electric field due to dipole at equatorial point. So E is magnitude of electric field due to minus Q or plus Q at that point. So from minus Q or plus Q, the point is at this much distance. Let's call it something, this R, okay, or this and this is different, or let's take something else. So let me call this distance as S. Okay, so distance S is equal to AP and it is also equal to distance BP. So I can write the electric field now. It is equal to 2 times of K, the constant, which is 1 over 4 pi epsilon naught, into Q over S square. Okay. Then sine theta from this triangle or this triangle, we can find the value of sine theta, which is opposite side. This is the opposite side, A divided by hypotenuse. So this one, which is equal to S. So we have A divided by S. Okay. So this is Q and this is A over S. Now, by Pythagoras theorem, we can find the value of S. So let's find it here. So I can write S squared is equal to A squared plus R squared, and therefore S is equal to the square root of that, A squared plus R squared raised to half. Okay. Now let's put those values here. So I can write the E equatorial is equal to 2 times K multiplied by Q divided by S squared into S is S cube. So this is S cube and multiplied by we have A. Okay. Now let us just erase this part. Yeah. Now let's substitute the value of S. So we have E equatorial equals to 2K into Q. Let me take the 2 on this side. So I will write this as K into 2 times QA. And now you know why I am writing it like this, or Q times 2A divided by S cube. So S is A square plus R square, or R square plus A squared raised to half, and cube of that. So we have 3 by 2. Okay. Now recall that the electric dipole moment of this dipole, which is directed from minus Q to plus Q, it has magnitude of Q into 2A. So recall that the electric dipole moment, which is given by P bar is equal to Q times 2A, and it will have some direction P cap. Okay. So magnitude is Q into 2A. We can write this term Q into 2A as P, the magnitude of electric dipole moment. So this is P divided by R squared plus A squared raised to 3 by 2. Or I can substitute the value of K also. So this is 1 over 4 pi epsilon naught into P divided by R squared plus A squared raised to 3 by 2. Now this is the value of electric field due to the dipole at equatorial point. Okay. Now let's find its direction. So direction of the dipole moment P bar is from minus Q to plus Q. It is in this direction, but our electric field, it is in this direction. So direction of dipole moment and direction of E bar, they are opposite to each other. E equatorial is opposite to the direction of P, and that's why if I put vectors on both sides, then I will have to put a negative sign over here. This is 1 over 4 pi epsilon naught minus P upon R squared plus A squared raised to 3 by 2. Okay, so this is the value of electric field due to a dipole at an equatorial point. Now let us find a specific case of this. So we will find the electric field at a faraway point. So we are interested in this case. When R is very large compared to A. And now you know what we are going to do. We are going to just neglect this A in the denominator. Okay, so we'll have E equatorial equals to 1 over 4 pi epsilon naught into this minus p bar divided by r squared raised to 3 by 2. So r raised to 2 multiplied by 3 by 2. So this 2 and 2 gets cancelled. So we have r raised to 3. Okay, so when r is very large compared to A, this A in the denominator or A squared in the denominator is insignificant compared to r squared, so we neglect it and we get this much value for the electric field. Now recall what was the value of electric field along axis of a dipole at very far away point. So let me tell you that value. E equatorial equals to K into P or R cube, and E axis or E axial is equal to K into 2P over R cube. So at faraway point, the electric field due to dipole is twice along the axis compared to the equator. Okay, so the intensity of electric field is more along the axis compared to the equator. Then let's compare this electric field with the electric field of a point charge, single charge. So electric field of single charge is proportional to 1 over r square. We know the formula. It is 1 over 4 pi epsilon naught multiplied by q over r squared. So it is inversely proportional to r squared. But the electric field due to dipole is much weaker compared to this one. It is inversely proportional to r cube. Okay, so let it be the equatorial point, the axial point, or any point. Electric field due to dipole is much weaker compared to the electric field due to a point charge. And you can draw the electric field. You can represent it pictorially. So electric field due to point charge we are drawing E versus R graph. So graph will be something like this. Okay, so this is for point charge. So if this is 1 over r squared, for a dipole, the graph will be something like this. It will be, the point is it will be faster. It will decay faster compared to this field. So it will be something like this. So this is 1 over r cube. And this is field of dipole. Okay, now I have not drawn these curves to the scale, but it should be clear that for dipole is the electric field decays much faster compared to the electric field of point charge. Okay, so this falls very slowly to 0. So it is something like this. Okay, now we are familiar with the electric field of dipole. Now let's move on to the next point, which is the effect of external electric field on electric dipole. So let us erase this part. Okay, so let's find the effect of external field on dipole. So, and we are interested in a particular external field, that is uniform electric field. Now we know that the strength of electric field is contained in the density of electric field lines. So if electric field lines are dense, the electric field is strong, and if they are rare, the electric field is weak. So how to show the uniform electric field? So uniform electric field is shown by a uniform density of electric field lines. So we draw these equidistant parallel lines. So they are equidistant and parallel to each other, and they represent the uniform electric field. So the value of this field, the magnitude, is same at each and every point of space. Now let's put the dipole in this field. So we put this dipole like this. So this is minus q and this is plus q, and this dipole is inclined at some angle to the electric field, and suppose that angle is theta. Okay, and theta is also the angle between the dipole moment, which will be directed from minus q to plus q, so it is along this direction, and the electric field. So theta is angle between dipole moment p bar and electric field. Okay, now there will be force acting on this plus q and minus q due to the electric field. So force on plus q will be directed like this in direction of electric field. Let's call this force F plus bar, and force on minus q due to the electric field will be directed like this. So this is F minus bar. Okay. Now because the value of electric field is same at this point and this point, the magnitude of F plus bar and magnitude of F minus bar will be same. So the magnitude of F plus bar equals to the magnitude of F minus bar, and we know that the force is equal to Q into the electric field, the magnitude of charge multiplied by magnitude of electric field. Now the magnitude of these forces F plus and F minus, they are same and they are directed opposite to each other. That's why the total force on dipole is 0. So F plus and F minus are directed opposite to each other. Therefore, net force on dipole is equal to 0. Okay. So the dipole will not be displaced in space due to this electric field, but dipole will rotate in space. It is because though the net force is 0, there is some torque acting on the dipole due to the combination of this F plus and F minus. And we know how to find torque. So torque acting on dipole let's call it tau. So it is, if both forces are same, then it is magnitude of one of the forces multiplied by perpendicular distance between two forces. Okay, the torque is magnitude of one of the force multiplied by perpendicular distance between the forces if two forces are equal, and if they are unequal, then we'll have to find out the torque separately and then we'll have to add it. Okay, in this case they are equal, so let's find the perpendicular distance. So this much is the perpendicular distance between these forces. This angle is also theta. Let's name these points. So let's call this A, this is B, and this is M. So perpendicular distance is BM. Now in this triangle, sine theta equals to this opposite side, BM divided by AB, and which implies that BM equals to AB sine theta. Okay, and AB is this distance, it is the length of the dipole. So this is 2A into sine theta. Now let's put the values of magnitude of force and the perpendicular distance. So this implies that tau, the torque, is equal to magnitude of force is Q into E multiplied by perpendicular force is 2A into sine theta. Okay, now let's group Q and 2A together. You know why we are doing this. So Q into 2A multiplied by what we are left with is E into sine theta. Now you know that this is the electric dipole moment. This is magnitude of electric dipole moment. So let's substitute P for it. So the dipole moment P equals to Q into 2A. Okay. So Q times 2A is the dipole moment. So we have P into E multiplied by sine theta. So this is magnitude of the torque. Now torque, as we know, is a vector quantity. So what about the direction of torque? So let's find the direction also. Okay, so on right hand side we have magnitude of one of the vectors, E bar is a vector, magnitude of the other vector multiplied by sine of the angle between two vectors. So on right hand side, either we'll have P cross E or we'll have minus of P cross E, that is E cross P. So we have to check whether it is P cross E or minus of P cross E. Let's check that. Now we have this dipole. So imagine that this is dipole, this is F plus and this is F minus. So in what direction this dipole will rotate if these two forces are acting on it? So it rotates like this. So for you it is in this direction, the clockwise direction. So if it is, the rotation is in clockwise direction, then using right hand thumb rule we find the direction of the rotation or direction of the torque. So curl your fingers in the direction of rotation, okay, and stretch your thumb. So it gives you the direction of torque. So it is inside of plane of this board. Okay, so the direction of torque is into the plane of board. Now let's check the direction of P bar cross E bar and minus P bar cross E bar. So P bar is directed like this. Let me draw it. So this is direction of P bar. This is direction of E bar. Now we know that if we take cross product, if I take cross product, that is P bar cross E bar, then the resultant of this, it is directed, its direction is found using the right hand thumb rule. So keep your right hand in direction of first vector, curl your fingers towards the second vector and through the small angle, so this one is small angle, and then stretch your thumb. So stretched thumb gives the direction of P bar cross E bar. So it is also into the plane of board. So the direction of P bar cross E bar is also into the plane of board, and direction tau is also into the plane of board. So we have solved the problem of direction of tau. So it is along P bar cross E bar, and its magnitude is exactly equal to P bar cross E bar. Therefore, I can write the tau in vector form. So tau in vector form is equal to P bar cross E bar. Okay, and its magnitude is tau equals to PE into sine theta. Good. So now we have found the amount of torque acting on dipole when it is kept in uniform electric field.